Next, let's look at how to find out the distance between a point which is given in space and a line which is also in the three-dimensional space whose equation is given to us. Now, if you remember from three-dimensional geometry, the distance of a given point x1 y1 from the line ax plus by plus c is equal to 0 was pretty straightforward. It is d is equal to ax1 plus by1 plus c divided by square root of a square plus b square. But in three-dimensional space, the equation of a line is not given in the form ax plus by plus c cz plus d or something like that. That is the equation of a plane. So therefore, calculating a general formula or deriving a general formula for the distance of a point x1 y1 z1, for example, from a given line x minus x dash upon a equals y minus y dash upon b equals z minus z dash upon c, would be a difficult thing to do, but then it is still possible. So therefore, the important thing to remember is not the formula that results, but the important thing is to remember the process which was followed to get the distance of a given point from the given line. So let's look at the whole procedure to find this. Let P given by alpha, beta, gamma be the given point, and let x minus x1 by a equals y minus y1 by b equals z minus z1 by c be the given line. So therefore, we have to find the distance between the point P and the given line. That is the shortest distance. And we know that the shortest distance between a given point and a line is the perpendicular distance. So therefore, we already know one thing about the shortest distance between the given point and the given line, that it is perpendicular to it. And we of course are going to use this fact. So how do we do that? Write the coordinates of a general point on the given line. So the coordinates of the general point on the line are x1 plus a lambda, y1 plus b lambda, z1 plus c lambda. Why? Because the equation of the line is given by x minus x1 by a equals y minus y1 by b equals z minus z1 by c. If we assume that this point L is the foot of perpendicular drawn from the point P on the given line, then we can write the direction ratios of PL. And we apply the condition for the given line and PL to be perpendicular. That is, the product of the respective direction ratios in the x, y and z directions added together gives us 0. So doing that, we get the value of lambda, and then we substitute the value of lambda in the coordinates for L, which is x1 plus a lambda, y1 plus b lambda, z1 plus c lambda. Note here that x1 and a, y1 and b, z1 and c are already known to us. We just obtained the value of lambda by applying the condition of perpendicularity. Now that we have discovered the value of lambda, we can just substitute and obtain PL by using the distance formula. So therefore, this is not a formula, this is actually a process which we use to find out the distance, the shortest distance between a given point in 3D space and the given line x minus x1 by a equals y minus y1 by b equals z minus z1 by c. It is possible to write down a general formula for this, but then the general formula would turn out to be very complicated to remember. Instead of that, if we just remember the process, then we can apply it to those particular cases which we are dealing with in actual numerical examples. So the illustrative diagram for the same is given as follows. So here we see that P is the point alpha, beta, gamma, and the line is given by x minus x1 by a equals y minus y1 by b equals z minus z1 by c. L is the point representing x1 plus a lambda, because we let x minus x1 by a equals y minus y1 by b equals z minus z1 by c is equal to lambda. Now lambda is a parameter, so lambda can take on any value. Now what is the particular value that we are looking at? The particular value which corresponds to the foot of the perpendicular from the point P. So for that we require to apply the condition that PL is perpendicular to the given line AB. So from that we obtain one particular value of lambda which corresponds only to the point L, which is the foot of perpendicular, and therefore that joined to the given point P will be the shortest distance between the points P and the line, and thus giving us the answer. So therefore L is x1 plus a lambda, y1 plus b lambda, z1 plus c lambda. Applying the condition for PL to be perpendicular to the line AB, we get the value of lambda, and from lambda we obtain the coordinates of the point L, and by obtaining the coordinates of the point L and applying the distance formula between the points P and L, we get the shortest distance between the point P and the line x minus x1 by a equals y minus y1 by b equals z minus z1 by c. So this was the Cartesian style of finding out the distance between a given point and a given line. Can we do the same in vector form? Yes, of course. Whatever can be done in Cartesian form can also be done in vector form, and vice versa. So therefore, if P alpha bar is the given point, and let R bar is equal to A bar plus lambda B bar be the given line, then what we do is we write the position vector of a general point on the given line, and so that's given by R bar is equal to A bar plus lambda B bar. Assume that this point L is the required foot of the perpendicular from P on the given line. So therefore PL is equal to position vector of L minus position vector of P. So that's given by A bar plus lambda B bar minus alpha bar, right? So therefore after we do this, then we know that PL is perpendicular to the given line, so PL bar dot P bar is equal to 0. So A bar plus lambda B bar minus alpha bar is equal to B bar. Again, applying this condition, we will obtain the value of lambda, and then we substitute the value of lambda back in the equation R bar is equal to A bar plus lambda B bar to obtain the position vector of the foot of the perpendicular L, and then find the, now that we know L, we can get the vector PL bar as the position vector of L minus the position vector of P, and from there we obtain the required length of the perpendicular from the given point P. And that is the procedure that we follow to find the shortest distance between a given point and a given line in 3D geometry. Let's look at some examples to help us understand this procedure much better. So here goes the first example of this type. Find the length of perpendicular from the point 1, 2, 3 to the line x minus 6 by 3 equals y minus 7 by 2 equals z minus 7 by minus 2. Therefore, let a point L on the given line be x is equal to 6 plus 3 lambda, y is equal to 7 plus 2 lambda, z is equal to 7 minus 2 lambda. So just to illustrate, suppose this is the line x minus 6 by 3 equals y minus 7 by 2 equals z minus 7 by minus 2 is equal to lambda, and this is the point P 1, 2, 3. Suppose L is some point on it. So therefore L can also be represented by 6 plus 3 lambda, 7 plus 2 lambda, and 7 minus 2 lambda. Okay, so therefore direction ratios of PL will be what? 6 plus 3 lambda minus 1, 7 plus 2 lambda minus 2, 7 minus 2 lambda minus 3. That is, they will be proportional to 5 plus 3 lambda, 5 plus 2 lambda, 4 minus 2 lambda. So the direction ratios of PL are this, and the direction ratios of the line to which it is perpendicular obviously are proportional to 3, 2 and minus 2. Now PL is perpendicular to the line x minus 6 by 3 equals y minus 7 by 2 equals z minus 7 by minus 2. So therefore, the corresponding x, y and z direction ratios are proportional to each other. When they are multiplied and when they are added together, they will get 0, not proportional. So we get 3 times 5 plus 3 lambda plus 2 times 5 plus 2 lambda plus minus 2 times 4 minus 2 lambda is equal to 0. So this gives us lambda is equal to minus 1 after solving. So therefore, we get the coordinates of the point L as x is equal to 6 plus 3 lambda is equal to 3, y as 7 plus 2 lambda, so that's equal to 5, and z as 7 minus 2 lambda, so that's equal to 9. Therefore, PL now, so these are what? Coordinates of the point L. Therefore, PL will be what? Square root of 3 minus 1 the whole square plus 5 minus 2 the whole square plus 9 minus 3 the whole square. So that's equal to the square root of 2 square plus 3 square plus 6 square. So that's equal to the square root of 4 plus 9 plus 36. So that's square root of 49. And therefore, PL, the shortest distance between the point P and the given line, is 7 units. And that's the answer.